Hi, welcome to Module 6 of Lecture 11. This is our third module covering how to solve linear equations, and this one is going to be devoted to the topic of matrix inversion. Okay. Before we actually get to the point of discussing an actual example of this, let's discuss a little more about matrices and how they relate to equations. Now, we already did this before in a previous module, and it's actually several previous modules, so let's be really quick. But recall that you can represent a system of equations that look like this. I'll do a 2x2 one because it's easier to write fast. I said fast, but that was a misnomer. 2 equals y1 equals y2. So there's a system of equations. I don't know why I put a parentheses around it. We can write this as x equals y. So you can treat, and again, if you don't see how this works, make sure you write out a, multiply a times the column vector x, and you see you get a column vector y. So this is a way of writing out this equation. I mentioned before that one useful thing to do with this was to understand the rank of the matrix, because it helps you understand how many sort of dimension of the solution space. We didn't really go into really clear details at the time. Part of that was because we're doing this later, so let's do it now. There's two things you can do with this representation. One thing is kind of boring because we just did it in the previous module, which is if you write this like this, you can write what's called a sort of expanded matrix, and get a sense of exactly, and manipulate the rows and columns of the matrix by using the exact same technique we did before. Manipulate the rows of the matrix. So we multiply rows by constants. We can add and subtract rows together, or multiples of rows together. We can reorder the rows. And the goal is to get a matrix that basically looks like the same upper triangular matrix that we had in the previous module for elimination. For elimination, we didn't actually draw the matrix out, but if you recall, we had elements that were just like a matrix. So the bottom one had, for that one it was x3 or z, but whatever, x3 equals a number, and then we had something plus some other constant, x3 equals a different number, and then we had x1, we could have this, x1 plus some number x2 plus some number x3 equals, I ran out of numbers this way, different number, there we go. So this form, which is the general form we had before for elimination, except now we have ones in front of the x's. This is a nice way of writing, we can convert this to a matrix rather. The matrix would look kind of like this, 1a, b, 0, 1, d, 0, 0, 1. If we stuck these in the same side here as a sort of expanded matrix, then this gives us a nice way of keeping track of our elimination, because we make sure we always we operate on the left-hand sides, which are over here, and the right-hand sides at the same time. And we can move around the rows, and we can add and subtract rows, and we get this form. This row echelon form over here allows you quickly to solve. So this tells you directly that x3 equals c. You can plug c times d, subtract that from e to get x2 quickly. Then plug in x2 and x3 to here, subtract from f, you get x1 easily. So really it's just a way of keeping track of elimination. If you like this, you can read more about it in the book or elsewhere. It's just really the exact same thing as elimination, except you put it in a matrix first, and then you go through and do all the same operations as in elimination on this matrix, making sure you do the same thing to each row at a time. And then you end up with this form, which is easy to solve. It's really no different than elimination. It just helps you keep track of things sometimes if you like it. So it can help you keep track of stuff. But given that it's the exact same thing as elimination, we're not going to talk about it too much, or at all anymore. Goodbye. Okay. What we are going to talk about is the other use of matrix representation for matrix inversion. Before we do that, let's take a brief side note about, and I'll write this over again, a brief side note about uniquely determined versus overdetermined versus undetermined, right? So the question is, how many solutions does your system of equations have? You can get at that quickly by looking at the rank of this matrix A. Now let's say that the rank of the matrix equals its number of rows. That tells you the system has at least one solution, at least one. It could have more than one, but it has at least one. Why? Well, in a nutshell, having a rank equal to the number of rows means you have all your rows are independent, linearly independent, so they're useful information for solving the system. And you have no more columns that are linearly independent than rows. You have more columns that are independent than rows, or the same number, which means you can solve for at least the number of rows, number of variables. Let me say that again, because that's a little confusing. So let's say you had, with an example this time, so let's say you had two equations and two rows, A11, but three columns. Well, that would mean two things. One, you have two equations, and if the rank of the matrix was equal to the number of rows, that means both rows are linearly independent. So that's good. That means you have two unique equations that can be used to solve for variables. And now you have, since you have the rank of the columns at least as much as the rank of the rows, you have at least two and possibly three independent columns, which mean you have at least two variables to solve for with your rows. So you'll find at least one solution and possibly more solutions if you have three variables to solve for. Possibly more than one solution. But you have at least one solution if the number of rows of your matrix equals the rank of the matrix. Now, if the rank of the matrix equals the number of columns instead, so you have this. So this is an example of that, not the only example, but an example. Yeah. Now you could have more rows that are independent, or more columns that are dependent, rather than more rows that are dependent. But let's just use this example for simplicity's sake. If the number of rows, if the rank of the matrix equals the number of columns of the matrix, then at least one of your rows is linearly dependent. Okay, right? Because the number of so you have, if you have a matrix like this or anything else that has the rank equal to the number of columns, then at least one of your rows, so either you have the same number of rows as columns, which we'll get to in a second, or you have more than that. But regardless, if the rank of your matrix equals the number of columns, then you have no more than one solution and may have none. Right? Because you have, when the rank of the matrix equals the number of columns, not rows, you have potentially rows that are dependent on each other if there are more rows than columns, or more total rows than independent columns. So you have some dependent rows, and if you have two dependent rows, like for instance this, right, this equation right here, those two rows would be the same, the two variables. And we know that either the right-hand sides are also dependent, in which case they're the same equation and there's no contradiction. So you can have a solution by just eliminating one of the rows completely. Now you get a solution. Or the right-hand side ones are not dependent in the same fashion, and you get a contradiction. So either you're going to have just enough equations to solve for all the variables that are given in the columns, in which case the rank equals the number of rows and the number of columns, they're the same, or the rank equals the number of columns, there are more rows than that, and some of the rows might be contradictory. If they're contradictory, you have no solutions. So going back, rank equals rows, number of rows. That implies greater than or equal to 1 solutions. Rank equals number of columns. That implies less than or equal to 1 solutions. Well, now what if you have the same number of rows and columns? So the standard square matrix. Well, if the rank is the same as both the number of rows and the number of columns, then you know all the rows and columns are linearly independent. In that case, so rank equals number of rows and number of columns, same time, then, I'm sorry, I should back up here. When I said number of linearly independent columns, I meant number of columns. So if the number of rank equals number of columns, then you have less than or equal to 1 solution. Now, if the rank equals the number of rows, which also equals the number of columns, so they're all linearly independent, then you have, it implies 1 solution only. So you get one and only one unique solution. Because you have the rank number of linearly independent rows. So the number of equations you have are all independent, and you have that same number of columns for variables. So you have the same number of useful equations as you have variables, and you get a single unique solution. So those are the 3 ways you can determine how many solutions you have by putting this into matrix form. Okay. So now, typically we're going to be using square matrices here for these things, and we wanted to know whether or not our square matrix actually has linear independent rows and columns. Well, if you recall from previous module, you can tell if the rows and columns are linearly independent by taking the determinant of the matrix for a square matrix. So what we do is take the determinant. If it equals 0, the matrix is singular. And if it's singular, right, A, you can't invert it, and B, the rank of the matrix does not equal the number of rows and the number of columns. At least one of them is less than the number of its total number, right? Either one or more of the rows is independent, or one or more of the columns is independent, or both, or whatever. So you have a singular matrix, and you don't have a single unique solution. However, if the determinant is non-zero of a square matrix, then everything's independent, it's non-singular, and you have one solution, one unique solution. And in that case, you can use the same technology to find that unique solution. And finally, we get to the point of this. If this is your equation, I change to B now. If this is your equation, you can solve for x by inverting your matrix. So I multiply the left side, multiply both ones by A inverse. I get this equation here. A inverse A is the identity matrix. The identity matrix times anything returns itself. So this thing is going to equal x, and then you have A inverse B on the right side. So you can solve for your solution, your x vector solution here, by inverting your matrix and multiplying that inverted matrix times the right-hand side of your equations as in vector form, and that'll produce the vector of solutions. There you go. Let's do 2 examples, one 2 by 2 and one 3 by 3. 2 by 2 is a bit harder. So 2 by 2 first. So let's have, again, x equals 1, y equals 2. We'll go through and do it backwards again to find the equation. Let's say 3x minus 7y and 5x plus 10y. These bigger numbers because 2 by 2 is easier. So we plug in 3 minus 14 is negative 11. 5 plus 20 is 25. Now, how do we do this? Well, the matrix A is going to be 3, negative 7, 5, 10. The matrix, the vector x is what we're trying to solve for. And the vector B is going to be negative 11 and 25. That's a setup. We need to invert A and multiply it by B. So what's A inverse? Well, first we need the determinant. The determinant of A is equal to 3 times 10 is 30, minus negative 7 times 5, so that's plus 35 equals 65. That's the determinant. The inverse of A is equal to 1 over the determinant. So 1 over 65. You flip these two, and you put negatives in front of the other ones. If you don't remember how to do that, go back and check out matrix inversion in the previous lecture. So it's 1 over 65 times this. You multiply it A inverse times B. That's going to be equal to X, your solutions. Well, what's that? That's 1 over 65 times 10, 7, negative 5, 3, times negative 11, 25. Again, I'm going to do this fast, but you should, at home, go through and make sure you can do this yourself. This makes multiplication. So 10 times 7, 10 and 7, dotted with negative 11 and 25, is going to equal negative 110. I'll just write it out because, hey, that's a big number. Negative 110 plus 7 times 25, that's 175. Yeah. Second one is negative 5 times 11 is 55. Plus 3 times 25 is 75. That equals 1 over 65 times 65 and 130, which magically equals 1, 2. Hooray, no math mistakes on the scale. Okay, there you go. So that's the way of using matrix inversion to do to solve an equation using matrices and vectors. The same kind of system of equations as before. Let me do a very simple version of the 3x3 because I don't want to go through and do a long multiplication sign because honestly it's not that important. There are examples in the problem set, but and the book as well. But let's just do a simple one. Let's say you have this again, and let's make a nice easy one as much as possible. Let's say x plus z and x plus y and y plus z. There we go. Let's see if that works. So this is going to be 4 and 3 and 5. Okay. How do we do this? Well, we can write it as a matrix first. Well, let's see. We have 1, 0, 1, 1, 1, 0, and 0, 1, 1. There we go. B is going to equal 4, 3, 5. So first, let's do the determinant. We can expand it any way we want to expand. Let's do the first column. So the determinant of A is going to equal 1 times the determinant of this, which is 1, times negative 1 to the I plus j. I and j are both 1 in that case, so it's 1. Remember, we're expanding along this row here, this column right here, rather. Plus negative 1 times I plus j. Here we're on the second row, first column, so that's negative 1. So we have minus 1 times 1. Then we get rid of the middle one, and the first column, second row, that leaves 0, 1, 1, 1. That's negative 1 equals 2. So determinant is 2. Again, that was pretty fast. You should go back at home and do this by hand. I just want to go through this a little faster than taking 20 minutes on this one, but it's great practice to go through by hand, and I have another example to try to make sure you can do this right. And importantly, all the relevant factors are in here in the right order so you can know where it's coming from. Okay, that's the determinant is a half, so we have 1 over the determinant in front. I need the minors for this thing. I'm regretting doing this already, so well, this shouldn't be too bad, it's just long. So what are the minors? They're the determinant of the submatrix. So what's that? Minor 1 is going to be, we did that already, that's that leaves us with this determinant, that's 1. Minor 2, I shouldn't say 2, I'm saying 1, 2. Minor 1, 2, we also did already, that's 0 minus 1 is negative 1. Minor 1, 3 is the 0. Get rid of these two. You get 0 minus 1 equals minus 1. What else are we doing here? It's minus 1. And now we do this. Now we do this one here. Is that right? Yes. Now 2, 1. Oh, it's backwards, right? This is 2, 1. That's 3, 1. Apologies. This is 1, 2 now. I'm doing my columns instead of my rows this time. 1, 2. Gets rid of this and this. That's 1 minus 0 equals 1. Minor 1, 3. Gets rid of these two as 1 minus 0 is 1. Minor, second, last, what are we doing now? I'm going to tell you all the place, aren't I? Sorry. Minor 2, 2 is this one, so you get rid of this one and this one. You get 1 minus 0 is 1. Minor 2, 3, I don't know why I did this way. Minor 2, 3 is this one, so that's 1. And minor 3, 3 is these, gets rid of these two, that's 1. So either 1 or minus 1. You have to then do the cofactors. That's negative 1 to the I plus j. So you're going to flip this sign. So I'll change these to c's now. This stays the same. This stays the same. You flip this one. Stays the same. You flip this one. Minus. You stays the same. This one stays the same. This one stays the same. This one gets flipped. And this one stays the same. Again, you flip the ones where the sum of the rows and columns are odd, and you keep the ones the same that are even. So there you go. Now you have a cofactor matrix. You want the transpose of the cofactor matrix to give the adjoint matrix. So we have the inverse is going to be 1/2 times 1, C11, C22, C33, C21 will go in the 1, 2 spot. C31 will go in the 1, 3 spot. C12 goes in the 2, 1 spot. C13 goes in the 3, 1 spot. C23 goes in the 3, 2 spot. I just missed something here. So I get going backwards. Let me start. Okay, so this is the, so 1, 2 is a 2 is C21. A inverse 1, 3 is C31. A inverse 2, 1 is C1, 2. A inverse 3, 1 is C1, 3. A inverse, well, that's right, I just forgot to do one of these, didn't I? 2, 3, I didn't do, no, I did that. Let me move on. C32 is C23. That's right, I didn't do 2, 3 over here. Ha. C32 is the flip of the minor. The minor here for the third column, second row, is 1 minus 0 is 1. You flip that, so it's negative 1. And this is going to be over here in 2, 3. There we go. We're going to multiply it by b to get 4, 3, 5. And this is going to give us the answer, which is 1/2 times the first one. 4 plus 3 is 7, minus 5 is 2. Next one, negative 4 plus 3 is negative 1. Minus 5 is negative 6. I think I messed up a sign somewhere in there. 4 plus 3. -6. Where did the sign go? I gotta check the sign for a second there. 4 minus 3 is 1, plus 5 is 6. That's 3. There's a sign error here in the middle here, because that should have been 4, not 6. Let me check that briefly. That should be adding 4 to the, no, it should all be different sign. See, this is what happens when you go on the fly, you can make mistakes. Again, I'm keeping this in here because, you know what, we all make mistakes, and it's good to see how to recover from them. So I'm going to keep this in here and show you that everyone makes mistakes and not edit it out. So, -1, so let's check this out. So this is the offending column here, the offending row rather, is, this is 2, 1 of the adjoint, so that's 1, 2 over here. Let's check 1, 2. What was 1, 2? Well, that was first row, second column. That gives 1 minus 1 is 0. That's -1. That's just fine. And 2, 2 is 1 minus 0, which is 1. That stays the same. So that's just fine. And this one over here is 3, 2. There's 2, 3, which comes from 3, 2 over here. 3, 2 was third row, second column. Get rid of these dudes. 0 minus 1. Ah, that's the mistake. That's a plus 1. Right? Because the last one we just did, the third row, second column is 1 minus 0 is 1. Oh, that's right. Hold on a second. No, I'm sorry. Yeah, I did it. So it's 0 times 1 minus 1 times 1 is negative 1. You flip the sign because it's an odd number. Row plus column is an odd number. That gives you positive 1. That's positive 1. So that means this is negative 4 plus 3 plus 5 gives you negative 4 plus 8 is 4. And that's 1, 2, 3. There you go. So again, I could edit that out, but I think it's useful to see how mistakes can be they both happen all the time and can be dealt with by going through carefully and checking to make sure you got all the math right. Frankly, I'm surprised I only made one mistake in this whole thing because seriously, that was really fast. I highly advise you to go back, go through all the minors and the cofactors by yourself. Don't rely on my doing it on the board here, and make sure that it works out the way it's supposed to. The reason I did this anyway, despite skipping a lot of steps, A, I don't have room in the slides for for all the steps, but B, more importantly, by having all the sub answers in there, you can use this slide to check each stage of your work. Okay? And that's useful because you just saw here, it's easy to make mistakes, right? It's happens all the time. No matter how long you've been doing this math, you will make mistakes. You make algebra mistakes, and it's important that you can go through and correct your mistakes and find where they went wrong. And don't panic. Just realize, okay, there's a mistake here. Let's go back through. Now you might ask, how would you go about finding a mistake if you had not already known the answers ahead of time? Well, what you do normally is you go back and you plug in your solutions into the original equations to make sure they all work out. If you don't have the solutions ahead of time, you should go back always and plug back into the equations to make sure you have the solutions correct. It's a way of checking your work to make sure that all the algebra you just did didn't go wrong. So that's why I'm keeping this error in this. I apologize for those of you who are really frustrated by this small error at the end there. Well, frankly, I'm surprised that it all went right before that. But that happens, and it's good to know how to both do it, how to check to make sure that you did it right, and if you did it wrong, how to go find the error and fix it. Here, because we wrote all the math down, I was able to identify that the error had to occur in this row. That minimized the checking. We only checked 3 things instead of 9, and we found the error pretty quickly, and we're able to fix it. And that's what you do. That's what you can do when you go back in and plug things in and see if you're correct or not with your answers. See, if we had got -2, we would have plugged it in and seen that 1 plus -2 is not 3 at all. So we would have found our answer quickly. Okay, so that's it for matrix inversion. I should say, just in closing, I don't see why people use this as a common thing if you're doing it by hand, because seriously, I don't find it easier to find the matrix inverse than I do to just substitute or maybe eliminate. That said, this is an incredibly useful technique when you're using a computational aid, right? If your program can solve for the determinant and take in a matrix inverse, then you can represent all of your systems of equations, of linear equations, as matrices, particularly if they're pretty big, and plug them into the computer, and it'll spit out A inverse for you, and frankly, it'll also multiply by B for you, and you have your answer very, very quickly. Much more quickly than if you're trying to do a bunch of algebra, even with a computer. So this is a great technique if you have a computer handy. Personally, I find it much less useful if you don't have a computer handy. Substitution or elimination tend to work faster, for me at least. However, if you're really great with matrices and you're really bad with algebra, this might work better. Anyway, there you go. That's matrix inverse. In the very last module of this type, we're going to talk about Cramer's rule, which involves only the determinants. So it's a little easier in the sense that you only do inverses, just many determinants, but harder in the sense that you do 4 of them. That's it for this one. Thank you very much.